Great. Perfect.
Okay, sir.
Let me see. Come back here. Okay.
Okay, we can start the presentation now. So, good evening, everyone. On behalf of Applied Photonics Initiative, let me welcome you all to the webinar series organized by API IISc Bangalore. API is a student consortium of these prestigious student chapters like IEEE Photonics Society, OSA, and SPI. We aim at bringing together the photonics community by organizing workshops, summer schools, research talks, and outreach programs to connect with the young and curious minds to science by demonstrating simple experiments. Before moving on to the presentation, I request everyone to keep the mics. So before moving on to the presentation, I request everyone to keep the mics muted. If you have any questions, please use the chat box or the raise hand option. Without delaying further, let's welcome our esteemed speaker for today, Professor Juejun Hu. It's an honor to have you here, sir. Dr. Hu is an associate professor at Materials Science and Engineering Department at Massachusetts Institute of Technology. He received his BS degree from Tsinghua University, China in 2004 and his PhD from Massachusetts University of Technology in 2009, both in material science and engineering. Prior to joining MIT, he was an assistant professor at the University of Delaware, USA from 2010 to 2014. Professor Hu has co-authored more than 100 referred journal publications. He has been recognized with several awards like SPI Early Career Achievement Award, the Robert L. Coble Award from the American Ceramic Society, the Vittorio Gottarci Prize from International Commission on Glass, and the DARPA Young Faculty Award. And the last in the list is NSF Career Awards, among various others. Today, he will be talking about the topic Seeing Glass in a New Light, Chalcogenide Photonics. Professor Hu, I request you to begin with the presentation now. Thank you so much.
Yeah, thank you so much with the introduction. So you can all hear me all right?
Yes, sir, fine.
Okay, great.
You can share your slides, sir.
And of course, before I start, I also want to thank Professor Gupta for his very kind invitation for me to give the presentation here. It's truly an honor for me to be able to address this audience. So start. Okay. So as you can see from the title here, I'm going to be talking about photonics based on the class of material called chalcogenide glasses. It's a unique class of materials that, of course, Professor Gupta. But before I go into more details about this class of materials, what I want to do is I will start to give you a little overview of the different research directions in my group. So the overarching theme in my group is that we are working on a new photonic materials and device architectures. In fact, okay, excuse me for 1 second. Let me try to close the door in my room. I'm sorry. Okay, now hopefully it's a bit better. All right, sorry. Okay, so like I said, the overarching theme in my group is to develop new photonic materials and devices for different applications. So what I'll be focusing on today is I'll be discussing about how to use Chalcogenide materials to enable integration of different substrates like polymers as well as 2D materials. And we are also using unique phase change characteristics to enable tunable photonic structures. And before I go into that, I will just spend a few minutes discussing about some other research directions that I'm not going to go into details in the talk. So one of the big kind of direction in my group has been a trend to use on-chip photonic structures to enable spectroscopic detection of chemical and biological species. So for that, spectrometer turns out to be a very important component that allows you to extract the light intensity as a function of wavelength or the optical spectrum. So conventionally, optical spectrometer relies on dispersive elements like gratings or prisms. Right? So what we have done is we actually devised a new architecture that we call the digital Fourier transform or DFT spectrometer that uses an array of optical switches to actually perform spectroscopic interrogation. Now, what's unique about this architecture is that it enables so-called exponential scaling. Means that every time you want to enhance the performance of the spectrometer, you just increase the number of optical switch. Every time you add one optical switch, you immediately double the spectral resolution and the spectrum coverage. Okay, so with that unique scaling, we were able to achieve much higher performance within small compact footprint, and that's also amenable to on-chip photonic integration. Now, as another example here, so we also explore other materials besides chalcogenides. And one example here is actually this magneto-optical oxides. So these are essentially garnet materials, and they are used as the cornerstone material to create optical isolators, which is a kind of device that allow light to pass through in one direction, but completely block light transmission in the other direction. Now, conventional isolators has to be made out of large single crystal garnets, so they are not really amenable to on-chip photonic integration. And what we have done in collaboration with Caroline Ross's group at MIT, as well as Leiby's group from UESTC in China, is that we develop a new way to monolithically grow these materials on a silicon substrate so that we can realize seamless integration of isolators with other photonic circuits. And we have also demonstrated using this technology on chip isolators with a performance that's actually on par with their bulk counterpart. So besides on-chip devices, another big issue we're trying to solve here is how to couple light efficiently into and out of on-chip photonic devices. And for that, we of course face the inherent challenge that for any on-chip waveguides, the mode field diameter is much, much smaller in the order of sub-microns compared to a light in, say, a fiber or in free space that has a much larger diameter. So to deal with this kind of big mode mismatch here, what we have come up with is a new, what we call optical freeform coupler for high-density integrated photonics or off-chip. But the basic idea behind that is that we can actually create this kind of freeform reflectors at the end facet of a waveguide, and such that when light comes in, this reflector not only redirect the propagation direction of light by 90 degrees, it also reshape the beam so that it can exactly match the size in optical fiber or in other media. So we envision that this technology gives us a universal interface to coupling light between different kinds of devices, on-chip waveguides, fibers, or even free space components. And also, compared to other technologies such as grating coupler, this approach offers exceptionally low coupling loss in the order of about 0.2, 0.3 dB. And this is also inherently dispersionless because it's based on optical reflection rather than refraction. So more recently, we have actually collaborated with the Capasso group at Harvard, and we have demonstrated actually a new on-chip optical trapping scheme where we use this kind of reflectors to actually redirect light to free space, and then use optical field to actually manipulate microscopic particles. So we foresee that there's a lot of other applications to use this kind of device as a universal optical coupling interface. Okay, finally, I'll talk a little bit about metal surfaces here. And specific for this particular application I'm talking about here, we are trying to essentially recreate a class of optical devices that's known as fisheye lenses. So conventional fisheye lenses is used to essentially capture panoramic images over a very large field of view, close to 180 degrees. And in order to capture image over such a wide angle without causing much aberration, it's actually required that you have to essentially use multiple optical elements to essentially split the light bending power over multiple surfaces and suppress optical aberration. Now, the challenge, of course, is that such a lens becomes bulky and very heavy. So instead, what we have been able to do now is that we created a flat fisheye lens by transforming a flat piece of glass into essentially a fisheye over 180 degrees. So the architecture is shown in this figure here. What we have is on the front side of the glass plate, we put a little aperture here. And when the light comes in at different angles, it will refract at the front surface and then impinge on different locations on the backside surface. So if you design the backside surface correctly, you can realize continuous high quality imaging across the entire 180 degree field of view. So there's something we actually experimentally demonstrated in the infrared. And this work has also attracted a lot of attention. And it was also ranked actually as one of the top 10 research in 2020 back at MIT. Okay, so now let me actually turn to the topic today about Chalcogenide photonics. So to start with that, the overarching question is, what are these chalcogenide glass materials and why do we care about them for photonic applications? So these chalcogenide glasses are essentially the amorphous compounds of the chalcogen elements. So sulfur, selenium, or tellurium. Now, unlike their oxide glass counterparts, they actually exhibit a number of unique optical attributes that underlies their applications in photonics. So today, I'll specifically discuss about 4 unique optical properties of this class of materials: infrared transparency, okay, large optical nonlinearity, integration versatility, means that they can easily be integrated on different kinds of substrates, and finally, phase change behavior, where they can actually switch their structures from amorphous to a crystalline state, and at the same time, modulate optical properties to enable the creation of reconfigurable photonic devices. So this is also how I'm going to divide up my talk. I will divide it into 4 different modules, where I specifically focus on a class of applications that leverage the unique attribute. Okay, so now let's start with infrared transparency. And we're now using them to realize on-chip chemical sensors. So we are all familiar with oxide glasses, right? They are optically transparent. This is a striking property that allows you to immediately see through windows and enjoy the view outside. This is also the exact characteristics that opens up many applications of oxide glasses in photonics, from lenses, prisms, to optical fibers and integrated photonic devices. However, if you move to longer wavelength regime, if you go to infrared or particular mid-infrared, turns out that these oxide glasses, they actually becomes opaque. So to show that, I'm showing you here, this is actually an image, okay? So once I present this image to the students in my class and I ask them to guess who this person is. So the answer I got from the class is that this is Morpheus from the movie Matrix. Now, obviously, I know that I'm not looking that good. Okay, this is actually my infrared selfie I taken using a infrared focal plane array camera. Now, what I want you to focus your attention on is on my glasses here. Now, these glasses made of oxide glasses, they are perfectly transparent and visible, but you see that they actually turn dark in the infrared. So they strongly absorb the infrared light. Why is that? That has to do with the structure of oxide glasses. Okay, so if you look at the absorption mechanism here in the infrared, the dominant absorption mechanism is actually due to optical phonons. So the vibrational frequency of the phonons can be approximated with this equation here in the model of a harmonic oscillator. We're approximating essentially vibrating atoms as masses attached to the end of a spring. So in this case, the vibrational frequency scales with the square root of k. This is a spring constant, or in other words, the strength of the chemical bonds. And m, this is the reduced mass of the atoms. So now, if you move from oxide glasses to chalcogenides, you now have this heavier constituent elements. So this increases the m in the denominator. At the same time, because the chemical bonds between the chalcogens is weaker compared to in oxides, you also reduce the K in the numerator. So the net effect is that this chalcogenide glasses has a much lower phonon frequency compared to oxides, and this underlies their broadband transparency in the infrared region. Now, quantitatively, we can take a look at this spectra here. On top, I'm showing this is essentially a wavelength scale, and at the bottom here, I use this gray bar to represent the transparency window in different materials. You see that silica is getting cut off at around 3 microns, but for chalcogenides, they enjoy a very wide transparency window all the way from visible to the long wave infrared. And this also overlays with many absorption fingerprints of different chemical molecules. And that's why these chalcogenide glasses are actually ideal material candidates to create on-chip photonic sensors. Now, how does this photonic sensor work? The principle we're using here is so-called infrared absorption spectroscopy. We have some kind of light source. We then pass through a device in the form of optical waveguide. And in this waveguide, the light can actually interact with the molecule through a so-called evanescent wave. Essentially, light field that's spilled out of the waveguide core, so they can directly overlap with the molecules in the ambient environment. And then when this interaction takes place, the molecules is going to selectively absorb light at some selected wavelength. So then finally, the optical spectrum as a function of wavelength is then detected using a detector or spectrometer. What I'm showing you here, this is one example of the transmission spectrum measuring methane gas. And you may notice that there's actually a number of absorption peaks that occur at selected wavelength. So using this spectroscopic absorption peaks, we can then ubiquitously identify the specific molecules with very high specificity as well as high sensitivity. So for this purpose, we have really created waveguide sensors that perform such as spectroscopic sensing. Now, what I'm showing you here, this is actually our layout of the sensor here, where we assume a spiral geometry. And we take the spiral geometry just so that we can have a compact footprint, but at the same time, we also have a long optical path length. Now, increasing optical path length will also increase the interaction between light and the molecules to be detected. So therefore, we can actually boost the detection sensitivity. On the right-hand side, I'm showing you actually a measure spectrum using the sensor here that clearly shows an absorption peak that's centered around 3.3 microns that correspond to absorption wavelength methane molecules. We have also measured the response of the sensor as a function of the concentration of methane, and we get this very nice linear relationship that's in agreement with the classical Lambert-Beer's law. So we can then use this kind of sensors to actually perform quantitative detection. Now, in the first prototype, the detector as well as the light source, they are both of chip components. So if you want to realize a chip-scale sensing platform, you want to integrate all these components alongside the waveguide sensor to create an on-chip photonic sensor. So as a first step here, we were able to integrate now mid-infrared detectors also on the same chip along with optical waveguides. So what I'm showing you here, this is actually what we have demonstrated. This is a waveguide integrated mid-IR photonic detector. This is made out of another chalcogenide material, lead telluride. But in this case, this lead telluride turns out it's a nanocrystalline material. It also has some unique characteristics, whereas grain boundary is inherently passivated. So even though it's a polycrystalline material, it does not compromise its photo detection performance. And because also it's a polycrystalline material, it can also be directly deposited on top of any kind of substrate to facilitate monolithic integration with our chalcogenide waveguide sensors. So what we have measured here by directly overlaying optical waveguides on top of a lead telluride photodetector, we were able to get a high responsivity, about 1 amperes per watt at the mean infrared wavelengths. And this also corresponds to a distant quantum efficiency of about 50%. So then our natural next step is try to essentially integrate such a detector along with the evanescent waveguide sensor to create an on-chip detector integrated sensor here for methane gas. So in this experiment here, we essentially put together this spiral-shaped waveguides along with on-chip detectors, and we then encapsulate everything with actually a gas chamber to allow continuous flow of different gas species. Using this detector, we were able to demonstrate real-time detection of methane gas down to a detection limit of about 300 parts per million. And this can be further improved if we were able to improve the stability of optic coupling between the light source to the on-chip waveguide to avoid any kind of intensity fluctuation due to this off-chip coupling process. Okay, so far we have discussed about integration of detectors with on-chip waveguides for sensing applications. What we are missing here in this photonic link is actually a light source. So like I mentioned, on-chip integration will be able to further improve the power stability and at the same time also create a chip-scale photonic sensing platform. So that's what we have been working on right now. In the second part of my talk, I will discuss about how we actually leverage optical nonlinearity in these Chalcogenide glasses to create different type of on-chip light sources for different applications. So now speaking of on source, especially for sensing applications, there are a few requirements it has to satisfy here. The first one here is spatial coherence. And that's because for sensing applications, we are using single mode waveguide devices. Okay, any kind of multi-mode waveguide devices means that different kind of modes they will interfere with each other, and they also have different overlap with external environment. So this makes quantitative determination of concentration of species very difficult. Now, in order to efficiently couple into such a single mode on-chip devices, it's actually important the light source has to be spatially coherent. Or in other words, they must have a very small module area to effectively match that of on-chip waveguide. So besides that, this light source also needs to have a broad spectral coverage. This is again important for sensing applications where you need a wide spectrum to be able to uniquely identify different fingerprints of the absorption species. Now, next part is high brightness, and this is instrumental in boosting the signal-to-noise ratio of the on-chip sensing devices. And finally, this also has to be small, fully compatible with on-chip integration, and has to be able to conform to a robust on-chip integration scheme. So now let's apply this criterion to see how all the different light sources would actually play in this scenario here. So the conventional sources for infrared, you have black body sources. The challenge there is that this actually has poor spatial coherence. So the coupling efficiency to on-chip waveguides would be minuscule. You also have light-emitting diodes. And these light-emitting diodes, they are also limited by the spatial coherence. And at the same time, the bandwidth is also limited. Now, one solution that's commonly adopted is actually tunable lasers. But for tunable lasers, in order to cover wide bandwidth, they are actually quite bulky and expensive. And they usually involve moving mechanical components like rotating gratings that also limit the ruggedness as well as the integration capacity with on-chip components. So that's why we're turning into a nonlinear frequency convergent here, where we're leveraging large optical nonlinearity in Chalcogenide glasses to convert the light at one wavelength to other wavelengths over a much broader band. But to do that, there usually some challenge we have to overcome here. One is that for the pump source, to trigger this large nonlinear interaction, it's frequently needed that the pump laser has to be pulsed. Okay, excuse me. They have to emit these ultra short pulses so that you can essentially squeeze the energy in a very short pulse to increase the optical power and hence the nonlinear interaction. But now, if you look at all these ultra short pump lasers, they're typically benchtop setup with a very large footprint that it cannot be integrated with on-chip components. Okay, so we need to find a way to actually combine this kind of bulky components with our on-chip platform. So that's why we have been actually collaborated with Juejun Luo's group at Xiamen University in China. So his group has actually pioneered an ultra-compact femtosecond laser pump source. It's essentially based on sexual absorber based on graphene materials, so that when the light is amplified and passed through a sexual absorber, you can essentially turn the light into a very short pulses, but at the same time maintaining a very small footprint. So what I'm showing on the right hand side here, this is actually a photo of the laser they have demonstrated here, and you can see the size here. This is only a few centimeters across. So this will then be the compatible with integration in compact sensor platform here. Now, next step is that we want to be able to integrate this light source efficiently with on-chip waveguide. So on the left-hand side here, I'm showing the fabrication process of the Chalcogenide on-chip waveguides. We use standard lithographic patterning coupled with plasma etching to create these waveguide structures. And we also shape the waveguides, in this case, to a zigzag structure to enhance the interaction length at the same time to preserve a small on-chip footprint. Now, one more feature I also want to mention here is that at the end facet of the waveguides, we also create inverse tapers of this chalcogenide waveguides along with a polymer taper here made of SUA epoxy. And with this kind of end facet couplers, we were able to significantly reduce the coupling loss from the fiber laser onto on-chip waveguides, which is beneficial to enhance any kind of nonlinear interactions. So to test the performance of the device, this is really quite straightforward. We couple this ultra-compact femtosecond laser source directly with a fiber mounted onto a photonic chip. And then on the opposite side, we use another fiber to collect light into optical spectrum analyzer so that we can actually measure the output spectrum of the light source here. Now, specific to the design of the waveguides, we have to be very careful about engineering the dispersion characteristics of the waveguide here. Because it turns out, for all these nonlinear processes, dispersion of waveguides dictates the phase meshing condition in the nonlinear interaction, and therefore it will also dictate what is the regime of interaction that will operate our device at. So what I'm showing you here, this is a plot of the group velocity dispersion as a function of wavelength, plotted for 3 different kinds of waveguides that has different width from 0.8 microns to 1 microns. So what we're seeing here is that for the 0.8 micron wide waveguides, it exhibits a large anomalous dispersion. But as you move to the wider waveguides, at 0.9 microns, you see the dispersion at the target operation wavelength almost vanishing here. So we have a 0 group velocity dispersion waveguides. And if you move on to 1 micron wide waveguides, then you actually have normal dispersion. So it turns out that if you operate the waveguide in an anomalous dispersion regime, you get the interaction of so-called self-frequency shift of the Raman solitons. And what happens here is that this ultra-short pulse, femtosecond pulse, when it couples to the waveguide, because of large light intensity, it starts to trigger stimulated Raman scattering. In Raman scattering process, essentially you're converting photons of higher frequency to photons with a low frequency. Now, because we have a very short pulse, due to the very short time duration, it means that in the spectral domain, it also gets broadened. It contains different spectral components. Right? So because of the dispersion, it means that the shorter wavelength component will start to pump via Raman interactions the longer wavelength components. So the net result is that you see that as the pulse propagates through the waveguides, you see a red shift of the spectral components. So using this mechanism, we were able to actually demonstrate a tunable Raman soliton laser. By controlling the pump power, we can actually continuously tune the output power, output wavelength of the pulse. Therefore, we can get essentially a tunable laser here. So on the right side is actually a measured data. You see that we pump at the wavelength about 1.56 microns. But then as you increase the pump power, you see that a distinctive peak starts to emerge that correspond to the Raman soliton. And this Raman soliton will then redshift as we increase the pump power continuously across the spectrum range of about 200 nanometers. Now, this allows us to now create a unique tunable light source that can actually scan across wide spectral range, but without any mechanical moving components. Now, one more thing I also want to mention here is that compared to other type of fiber-pumped Raman soliton laser, our on-chip waveguides features much stronger light confinement to amplify the nonlinear interaction, and as a result, we can achieve a tunable laser with much lower pump power. So the pump power of this laser is in the order of a picojoule. This is 3 orders of magnitude lower compared to their counterpart in a fiber platform. So again, this is also beneficial if you're trying to create on-chip sensors with a low power consumption. Okay, so that's one type of a light source here. That's a tunable laser. Now, if you move on to this 0.9 micron waveguides, where it exhibit 0 group velocity dispersion, then what happens here is that it's going to trigger, instead of Raman soliton, rather a super continuum generation that cover broadband. So this is what we did here. We actually use this kind of waveguides to actually generate a broad super continuum that covers from about 1.4 microns all the way to beyond 2 microns and half wavelength, a half octave spectral range, so they can enable broadband spectroscopic interrogation of photonic sensors. And what we're seeing here is as you increase the wavelength or increase the pump power, you can of course extend the spectral coverage of the supercontinuum. And ultimately, the spectral coverage is actually limited by the power output from our compact pumping source. Okay, so this is one of the trade-offs here. You have to go, if you want to be larger wavelength coverage, you have to go with a desktop femtosecond laser that offers much more power. But again, that defeats the purpose of on-chip integration. So our next step is that we can use this supercontinuum source to actually demonstrate sensing applications. So for example, what we're doing here is we take chloroform as a model molecule, which exhibit absorption peak around 1.7 microns. So now if we pass our supercontinuum through in the media that contains a chloroform solution, what we're seeing here is that the supercontinuum spectrum now exhibit a little notch that's induced by absorption of these molecules. We can further fit the absorption data to a classical Lambert-Beer's law, and what we find out here is again the attenuation of the supercontinuum also follows the classical Lambert-Beer's law. So this now allows us to actually perform quantitative integration to determine the concentration of different chemical species. All right, next, I'm going to switch gears a little bit. I've been talking about the unique optical properties of these chalcogenide glasses. Now, another attractive attribute of this material is their integration versatility. Means that they can be easily integrated onto different substrate platforms to realize different applications. So for that, I'll talk about two different examples here where we can integrate on polymer substrates to realize mechanical flexible photonics, as well as on 2D materials to enable wide class of photonic components in this emerging 2D materials. So to start with, I want to explain why chalcogenides are actually attractive for so-called substrate agnostic integration. Means that they can be easily integrated on virtually any kind of substrates. So first of all, these glass materials, as their name suggests, right, they're amorphous. So it means that you can actually grow them or deposit them on any kind of substrates without having to worry about lattice measuring constraints. Now, more importantly, these materials can also be deposited while keeping the substrates at room temperature all the time. This again has to do with the unique bonding nature in these chalcogenide glasses. Right, compared to oxides, like I mentioned, these chalcogenides has weaker interatomic bonds. Okay? So as a result, when you're trying to do vapor phase deposition, it takes much less energy to actually break these chemical bonds, so that the thermal loading on the substrates also becomes significantly reduced. So this attribute means that we can actually process these materials at room temperature. This is important for applications such as integration of polymer substrates, where you don't want to cook these substrates. Okay, this is also critical for integration of different substrates, because turns out one of the biggest limitations for integration of different substrates is actually the thermal stress. Right, thermal stress usually causes delamination and weakens the interface between the film and the substrate. Now, with room temperature deposition, we can completely circumvent the issue of thermal stress and therefore get good adhesion between chalcogenides with a diverse range of substrate platforms. Now, of course, like I said, we can also fabricate these components of chalcogenide glasses using well-established microfabrication techniques. As one example here, we will fabricate waveguides with a low propagation loss and also cavity quality factor exceeding 1 million in optical resonators. Okay. So that's important for many applications here. And last but not least, these chalcogenide materials, they are also chemically stable. And this inertness is actually important. And as I'll show you later, they can also even function as a passivation coating for some of the less stable 2D materials. Okay, so these are truly multifunctional platforms. They not only carries optical functions, but also a passivation capability here. Okay, then we start by looking at integration into flexible substrates. So what we were able to do, this is back in a few years ago, where we demonstrated monolithic integration of chalcogenide devices on a flexible substrate. And we're also able to realize extreme mechanical flexibility here. We can actually essentially bend these devices down to a small bending radius, down to about 0.2 millimeters, essentially folding in half. We can also exert mechanical deformation over hundreds and thousands of cycles without seeing a mechanical property degradation. So while this is great, these devices were actually created on epoxy substrates. So they're bendable, but they're actually not stretchable. Now, for many photonic applications, such as conformal integration on like curved substrates, such as lenses or human skin, You not only want the device to be bendable, you also want it to be stretchable. Okay. Now, to create stretchable devices, our inspiration comes from the design of a spiral spring here. Right? By structuring stainless steel into helical shape, you can transform this rigid material, stainless steel, right, in bulk form, into something that can be easily stretched and deformed with a very large deformation. So what we did is that we essentially create an on-chip photonic spring here. So we were able to create this kind of waveguide with a serpentine geometry. And our mechanical analysis found that when you actually stretch such a structure, it is going to deform both in plane and out of plane. And in the process, relaxes most of the stretching deformation. Now, besides this kind of serpentine waveguides, we also have some critical photonic components that we do not want any mechanical deformation at all. Okay? So the example here will be, for example, grating couplers as well as resonators. Right? Because when you actually stretch on these components, you're going to change, for example, the pitch of the gratings, and this will actually change the operation wavelengths of the devices. That's not desirable. So that's why we also create locally stiff islands by patterning these devices on a stiff epoxy material. So by doing so, we essentially prevent any local deformation on these critical components. And then we link these components using the serpentine waveguides to create a photonic circuit. So by using such architecture, we were able to create actually stretchable photonic devices with a very large geometric deformation capability. We can actually stretch to a relative elongation of over 40%. And we also see that this device can also sustain repeated 3,000 deformation cycles without any appreciable change of the optical performance. Okay, so now we have this kind of flexible and stretchable photonic devices. But if you look at the topological configuration, they're essentially still two-dimensional. For some applications, it is actually desirable that we would extend the geometric configuration of devices into a three-dimensional space. So for such a 3D integration, conventional fabrication techniques would be quite challenging there because they are all planar fabrication methods. So our idea is actually derived from the configuration of a pop-up box. Right? In a pop-up box, all the structure is essentially planar, but when you actually apply this geometric deformation, then this 2D structure will then transform into a 3D configuration. So what we're doing here is we take the idea of a deterministic deformation of 2D structures. Right? We started with a planar device. Now, more specifically, we created essentially a set of little bridges that connect two rigid parts. We can embed different kinds of photonic components in these bridges here. And when we actually apply a compressive stress on the two ends, now these bridges is going to buckle in a deterministic manner. The shape of the buckle can be precisely controlled by modulating the thickness of the bridge across the length. Okay, so by doing so, we can get a three-dimensional structure and position different photonic devices at the predefined locations in a three-dimensional space. So some of the applications we're looking at here is actually stress mapping in three-dimensional tissue models. Okay, turns out this is actually a big challenge there, and people actually want to know how the stress is changing as the tissue evolves. It also changes how the cell will actually develop in such a tissue model here. Now, conventionally, this is usually done by using so-called 3D traction microscopy, essentially a variant of confocal microscopy that allows you to look at different sections of the tissue here. But this technique obviously doesn't apply if the tissue is actually opaque or translucent. There's also been some other techniques by using essentially flexible devices created on a two-dimensional substrate, try to map the stress in such a tissue here. But again, because of two-dimensional nature, you will not be able to get a truly three-dimensional stress distribution. So that's why we have proposed this technique to create a three-dimensional structure and then embed it in a three-dimensional tissue model. So what I'm showing you here is essentially a fabrication process in more details. We started out with a lithographic definition of this bridge patterns. We then create different kinds of photonic devices on the photonic bridges. And in particular, we created resonators so that we can, by looking at the resonance shift, we can monitor the local strain and stress in the three-dimensional tissue. We then delaminate this substrate using water-soluble tape from the handler substrate here. We then mold them on a mechanical motion stage. And then we use essentially microcontroller to precisely control deformation during the buckling process. And after that, we then get an array of little mechanical sensors that now can be embedded into a three-dimensional tissue model. So through a collaboration with Xinqiao Jia's group at University, we were able to embed this three-dimensional waveguides into a collagen matrix that's populated with cells. And we were also able to actually monitor essentially the variation of strain during the growth and differentiation of the cells throughout the entire 2-week period to get three-dimensional distribution of stress during this process here. Okay. So if you want to learn a bit more details about the fabrication process of sensors, I've included the reference here, and we are expecting to publish our results on the three-dimensional stress monitoring pretty soon. All right, in the next example here, I just want to mention that besides integrating polymer substrates, this substrate agnostic capability of Chalcogenide also foresees integration on a wide range of emergent 2D crystals. Now, the motivation behind this work is that if you look at conventionally how people actually integrate 2D materials onto photonic platforms, they all use a process of so-called hybrid transfer. So in a hybrid transfer process, what you will do is you start out by fabricating these photonic structures, photonic circuits. Then on top of that, you then transfer these 2D crystals onto the photonic structures. Now, the challenge with this kind of hybrid process is that one, because substrate now actually contains this rugged morphology. Okay, so when you're trying to transfer this atomically thin crystal onto this kind of structure here, then you tend to rupture at the edges of the topology here, and this will compromise the yield of such a process. Also, for this kind of hybrid process, the 2D crystal always reside outside the waveguide core. So any interaction with the 2D material will now rely on evanescent interactions, which is much weaker compared to confined mode inside the waveguide core here. Now, last but not least, any kind of hybrid process will have a limited throughput and integration capacity that's usually not desirable for manufacturing processes. So that's why we are looking into alternative using monolithic integration. So if we can actually start by growing the 2D materials on the substrate, and then instead of transferring them into a foreign substrate, we can stack on top different photonic layers. This would then be compatible with high volume photonic manufacturing, and it also enables flexible configuration of the devices as well as superior alignment accuracy that allows us to leverage photolithography methods to align the 2D structures with the photonic circuit on top. So despite all these benefits, the monolithic process was not demonstrated because of one big issue there. These 2D crystals, turns out they are pretty fragile. So if you're trying to deposit any kind of dielectric material on top, they tend to degrade, simply resulting from the deposition process. So this is actually what we started out, we tested with different kinds of materials. We started out with silica and titanium dioxide. They are common materials for passive photonic integration. But what we found out here is that if you deposit them directly onto a graphene substrate, if you look at the Raman spectra here, at the bottom, this black curve is the pristine graphene after the growth. It shows essentially a defect-free signature. But if you go on into this dielectric material deposition, then what comes up is this little peak here, this D peak, that actually corresponds to a generation of defects in the graphene material. If you measure now the transport property of the graphene after deposition, you also see a severe degradation of the mobility after material deposition. So again, this comes from the fact that this deposition process usually involves elevated temperatures and hence much significant damage to underlying graphene substrate. Now, one way to solve that, of course, is using atomic layer deposition, but the challenge there is that the throughput is very low, so you cannot deposit optical thick film for photonic integration. Now, this is where Chalcogenide come in. Again, like I mentioned, because they can be processed at room temperature, this very low thermal budget minimizes any kind of structural disruption with the underlying 2D material. So in the case of graphene here, we see that the deposition of Chalcogenide does not disrupt any of the underlying graphene substrates. And also, they actually also maintains the high mobility in these graphene materials without changing any of the inherent structural properties. And this characteristics applies not only to graphene, okay, it also applies to any other kind of 2D material we have tried in the process. So we tested different type of 2D materials ranging from transition metal like chalcogenide to black phosphorus to 5 fixed compounds as well as hexagonal boron nitrates. And in all cases, the material property of the 2D crystals is not compromised by the deposition of the chalcogenide. And in fact, they not only can preserve the unique attributes of the underlying substrates 2D materials, they can even serve protection layer to prevent chemical degradation of some of the less stable 2D materials. So just one example here, this is actually black phosphorus. This is a narrow gap 2D crystal that's quite attractive for infrared detection. But the problem there is that it's not stable. If you leave them in ambient environment, what's going to happen is that essentially it transforms in a few days from phosphorus to a puddle of phosphorus oxide due to the interaction with oxygen and so humidity in the ambient environment. So this is what we did here. We put it, and that if you look at the crystal, of course, after a few days, then all the crystal signature disappears in the Raman spectrum here. Okay. Now, if you coat it with a thin layer of chalcogenide glass film, then this material can actually even withstand very strong oxidants, such as hydrogen peroxide. So after putting the coating, we actually expose the material to a hydrogen peroxide, and there's essentially no change of the Raman spectrum here. See, showing that this coating of chalcogenide glasses can indeed stabilize this chemically unstable black phosphorus material. So what we are saying here is that this chalcogenide glass material is truly a multifunctional integration platform with 2D crystals. They not only allow you to realize broadband light guiding, okay, they can also passivate these 2D crystals. And we have shown one step further is that these materials, they can also serve as necessary gate dielectric to allow direct electrostatic gating to change the Fermi levels in 2D crystals to dynamically modulate their optoelectronic properties. So due to the time limit, I won't go through into all the details here. We have actually demonstrated a wide range of different photonic devices using this chalcogenide glasses on 2D crystal platform here. And I will certainly welcome you to refer to our paper to look at more details of how this integration process was executed. Now, I also want to mention that besides integration with polymers and 2D crystals, my group has also leveraged this substrate agnostic integration capacity to realize a wide range of photonic devices on other kinds of substrates, such as infrared crystals to enable metal surfaces, okay, in the infrared wavelength, on magneto-optical crystals to enhance the performance of optical isolated devices, as well as 3-5 semiconductors to realize hybrid integration of flexible waveguides with actually 3-5 photonic detectors to enable a fully integrated, flexible photonic integrated circuit. Right, so now let me switch gears and go to the last part of my talk, where I will actually give you a quick overview of the phase change behavior in this chalcogenide compounds. So in this chalcogenide compounds, you can actually switch them from amorphous state to crystalline state. In the process, there's also a very large optical property change. Okay, this is useful to create a reconfigurable photonic devices. And in the switching process, this is usually done using either optical or the electrical pulses. Okay, so to switch from crystalline state to amorphous state, what you will do is you're sending a large pulse with large amplitude, but very short duration. So by doing so, you elevate the material to above the melting point, and then you quickly quench down so that you can essentially preserve this kind of liquid-like amorphous state. Now, if you want to go in the reverse direction, you send in an energy pulse that's long in duration, but smaller in amplitude. So this will raise the temperature of the material to above the crystallization point, but below the melting point, so that all the atoms now have enough kinetic energy to move around and find the thermodynamically structured state, which is the crystalline state. Okay, so this is a reversible switching material. Now, like I mentioned, there's a very large electrical and optical property contrast because you change the bonding configuration during the structure transition here, and as a result, this is why they're quite useful as a reconfigurable photonic devices. Now, I do want to mention that this is not a new class of material. If you look at it, people have already used them in rewritable CD and DVDs, as well as the optical electronic memory devices. Okay. However, all these conventional phase changing materials, they're actually optimized for applications in a data storage applications, right? Not for photon applications. And the biggest challenge there is that these conventional materials, if we look at optical properties, especially in the crystalline state, there's actually very strong optical absorption, comes from free carrier absorption here. So that makes this material optically opaque in the infrared. And this makes any kind of optical applications quite challenging just because of this very large optical absorption. Now, my group, we pioneered the first phase changing material that actually exhibit broadband optical transparency across both amorphous and crystalline state. So the optical constant we measure on the left-hand side figure here, you see that it exhibits a very large optical property change from amorphous to the crystalline state with the index change about 1.5, which is huge. Okay? But at the same time, the material exhibits optical transparency across pretty much the entire mid-infrared to long-wave infrared wavelength range. Now, this broadband transparency now allows us to create a diverse range of optical devices that can be capitalized on the bi-state transparency. Now, to show you how we actually integrate these devices into a reconfigurable photonic platform, I want to explain how we actually switch the phase of this material reversibly. So the most convenient method for photon integration is to directly use doped silicon as a heater to actually pass current through and then use dual heating to trigger the phase transition. So what we're doing here is that essentially we're controlling the duration and amplitude of the voltage pulse. We can control whether we are crystallizing the material or we are amorphizing the material. Now I'll play a little video here that essentially shows the reversible change of contrast in this little patch of material here. This is actually our phase change alloy, and this is triggered by essentially applying current or voltage path across microheater here. Okay, so now with this kind of a switchable material, our application here is to actually create a reconfigurable metal surface optical device. Now, I just want to explain a little bit about what metal surface optics is. Okay, so if you look at conventional optical devices for free space components, it relies on this surface curvature to bend the property in the direction of light. Right. So, for example, this is a lens. Your curved surface creates essentially a phase delay that shows in this diagram here. Now, this phase delay then essentially bends the wavefront of propagating light. Then it creates a converging light rays that focus on the focal spot. Now, in the case of metal surface, what we do is we pattern an array of sub-wavelength antennas on the flat substrate. If you engineer the shape of this antenna carefully, you can impart phase delay on the light coming in at different locations, and then reproduce the same phase delay that resembles the case of a conventional optical lens. Now, as a result, this metal surface will then behave exactly in the same way as a conventional lens. It's going to distort the wavefront and then create a converging light rays. So what we get here is essentially a metal surface lens or metal lens. So using our phase changing materials, we then were able to create this electrically reconfigurable metal surfaces. Okay, so as one first example here, we have this kind of metal atoms arrayed on the heater here. If you measure transmission spectra when we switch between amorphous and crystalline state, you see a fairly large optical contrast coming up, just coming from the large refracting index change of the material. What we've also demonstrated is that besides switching between the fully crystalline and the fully amorphous state, by controlling the electrical pulsing here, we can actually also control the fraction of material we are crystallizing here, and therefore we can realize essentially quasi-continuous tuning across a very wide wavelength range. So in this particular example here, we were able to create 10 distinct optical states that correspond to a mixture of the amorphous and the crystalline phases with different volume fractions. And we also were able to continuously tune across a very wide spectral range, almost 500 nanometers. Okay, this is also the largest spectral tuning range people have demonstrated in such an on-chip metal surface device. And also, because we can integrate this kind of devices on the doped silicon platform, it becomes pretty convenient to create this kind of pre-packaged switchable metal surface here. And using this technique, we were able to actually create, in this case, a reversible beam steering device that can switch between the two different states that steer the beam from two different angles. Okay. Now, what I want to do is I want to give you another example here that shows how we can actually leverage this phase changing capability to create a functional device with optical capability. Okay, so in this case, this is actually a very focal metal lens that can actually switch the focal length when we switch from one state to another state. So the design principle of such a lens is that we need to come up with different kinds of designs of the metal atoms or the unit cells in such a metal surface. Okay. So what we did was come up with a total of 16 different metal atom designs. Okay. Now each of these metal atoms is going to impart different phase delay in the amorphous and in the crystalline state. Okay. So what we're doing here is we're encoding this phase delay using different color codes here. Okay. So red color essentially means 0 phase delay, yellow is half pi, green is pi, and then blue is 1.5 pi. So this covers a full 2 pi phase range. Okay. Now, if you look at the amorphous state phase delay here, we group these 16 metal atoms into four different groups. Okay. Within each group, you see that the metal atom exhibits the same color here in terms of phase delay. So it means that each of the group would exhibit essentially the same phase delay behavior in the amorphous state. Now, if we switch to crystalline state, you see that within each group, 4 different colors will show up, indicating that we can now translate the same phase delay in the amorphous state into a full 2 pi phase coverage in the crystalline state. So now with the combination of all 16 phase metal atoms, we can now cover this full 2 pi phase range in both amorphous state and the crystalline state. So using this approach, we can now create essentially arbitrary wavefront in the amorphous and the crystalline state and realize binary switching between arbitrary photonic functionalities. So of course, we can use that to actually create a very focal metal lens that switch from one focal spot to another focal spot. And we then fabricated this actually metal lens using our GSST phase channel material. And we also realized that we can actually have very high quality focusing with very large contrast between these two states here. And with it, the focal spot is also at the diffraction limit, indicating that this lens creates essentially no optical aberration during the re-switching process. Now, just as one way to imagine how we can actually apply this technology here, we actually demonstrated that we can use such a very focal metal lens to realize multi-depth imaging. So what we did is we placed two optical targets with containing different kind of patterns at 2 different depths that coincides with the focal plane of these 2 objects. If we switch this lens from between these 2 focal states, what we're seeing here, we are seeing only one object at a time when it's situated at one of the optical states, with very little crosstalk from the other state here. And we also characterize the resolution of such a metal lens, and we find out that indeed it can actually achieve the diffraction limit, again indicating that we can realize aberration-free imaging using this kind of switchable metal lens. So takeaway message, we have now realized a reconfigurable material platform that can achieve different kinds of tunable photonic devices by implementing a phase change onto the chalcogenide compounds. Okay, so just to summarize here, I discussed about 4 singular optical attributes of these chalcogenide materials. And we show that using infrared transparency, we can then create on-chip spectroscopic sensors to realize detection of different chemical species. We also leverage the large optical nonlinearity to achieve on-chip light sources that can be potentially integrated with sensors to realize a fully integrated on-chip sensing platform. By capitalizing on their substrate-agnostic integration capabilities, we then demonstrated integration of these materials with both 2D crystals as well as flexible substrates. And finally, I want to mention that these chalcogenide compounds can also be used as a cornerstone for any kind of reconfigurable photonic devices by capitalizing on their phase change characteristics. So now before I end, I also want to thank all my collaborators here. Of course, without them, we would not be able to realize all this wide range of photonic devices. So all the bulk chalcogenide compounds has been synthesized by our collaborator Kathleen Richardson's group at UCF here. For infrared spectroscopy, we've been working with Anu Agarwal's group at MIT. For the nonlinear on-chip sources, we work with Zhengqian Luo's group at Xiamen University in China, where they provide these ultra-compact femtosecond laser sources. For femtosecond photonics, we've been working with Nancy Lu's group at UT Austin, where they perform all the mechanical designs, and Xinjiao Jia's group at University of Delaware to realize integration of 3D photonics with the tissue engineering model. 2D material integration, all the 2D crystals are grown by Jin Kong's group at MIT. And for the phase changing materials, we have been collaborating closely with Vladimir Limmerman and Stephen Vitel's group at Lincoln Labs to realize integration of the switching materials with a standard photonic manufacturing platform. Okay. And last but not least, of course, we also work with Hualiang Zhang's group at UMass to create all the diverse reconfigurable meta surface design using machine learning techniques. All right, finally, I of course also want to acknowledge the hardworking students and postdocs in my group. Without them, we will not be able to realize any of the devices here. So this is a picture of my group, obviously taken from pre-COVID days, which we all admire and miss. Okay. Now, specifically, Qing Yang, he is a postdoc in my group that actually developed all the nonlinear sources. And Skylar, he was a former student, actually devised all the 2D photonic devices. Now, when it comes to creation of the 3D photonic structures, this is done by my student Jerome, as well as my student Sarah. And in terms of the phase changing materials, Yifei and Carlos are the inventors of this new low-loss broadband transparent phase changing material, GSST. And finally, Tian Gu is actually the designer behind all these creative meta surface devices. And Misha, he's a postdoc that's not only very good at fabricating high-performance meta surfaces, but also excel in creating very nice artistic renderings of different kinds of photonic. And that's why he's appointed as the Chief Artistic Officer or CAO of the group. So finally, this is the guy that actually really does nothing and just get to talk about it here. Okay. So with that, I'm going to conclude my talk, and I'll be happy to take your questions. Thank you.
Thank you, Professor JJ, for this wonderful and informative talk. I would now like to open the stage for question answer session. If you have any question, please unmute yourself and ask the question.
I have a question.
Mm-hmm.
Yeah. So in the varifocal meta lens that you showed, what is the minimum and maximum focal length that you could achieve?
Okay. Good question. So in this case, the minimum focal the focal length we are switching in this particular case here is, I believe, between 1.5 millimeter and 2.5 millimeter, something in that range. I don't remember exact numbers. In principle, we can realize arbitrary switching between any kind of different wavelength, because, like I said, we were able to cover a full 2-pi phase range in both structure states. So that means that we can switch between any kind of two different functionalities. Now, in practice, of course, ultimately, this is limited by the numerical aperture of the lens, right? So if you go to a very, very small focal length, then the NA or numerical aperture of the lens gets very large, and the focusing efficiency is going to get compromised. So that's the main limitation there. But otherwise, in principle, we can switch between arbitrary optical states, right? Not just lenses, but between lens, gratings, polarization splitters, anything.
Okay, thank you. And another quick question, like in a transparent doped silicon heater, there you showed the contrast was changing. What is the time scale of that change?
Okay, good question. It depends a bit on the material we are talking about here. So if you are talking about GSST, this is kind of the material we use here. Typically, we use about millisecond pulse. So the fastest switching speed we realized for crystallization is about 0.5 millisecond. For amorphization, it's much quicker. We can do it within a few microseconds. Okay. Now, some other materials we're also looking at here. For example, we tried antimony stellite, SB2SE3. For that one, we can realize switching in about 10 microsecond time scale for both crystallization and amorphization. So it depends a bit on the material.
Okay, thank you.
I have one technical question about the femtosecond laser source that is very compact. May I know the details, like specification of the pulse? Like,
sure. In fact, what I would do is that this is actually not my area of expertise. So what I would do is actually I would refer you to this paper here. And you can also get in touch with my collaborator, Zhengqian Luo's group at Xiamen University. He is kind of corresponding also of this paper. They also have a little startup company that actually sells this kind of femtosecond laser source if you're interested. So,
okay, it's available in the market. Like,
it's available in the market. They have different kind of type of things. Yeah, so you can directly contact Professor Luo. Yeah.
Okay, thank you.
JJ, I have one quick question on the temperature stability of these chalcogenide GSSTs. What is the maximum temperature that it can withstand or something? Because do you know what the temperature stability, how long, what temperature maximum it can withstand? For example, the very
So it depends, of course, depends a bit on duration. So to trigger crystallization, we usually do it at about 250 degrees Celsius. For at that temperature, it's probably like a few minutes. If you go to slightly high temperature, you can expedite the reaction, right? It can go down to like half a millisecond, like I mentioned.
Okay.
So that's for the amorphous phase. So you can pretty safely use them below like 200 degrees Celsius. Nothing is going to happen. For the crystalline state, it's thermodynamically stable. So you can heat them up all the way up to like melting point, which is around 600 degrees Celsius.
Okay. And for these varifocal lenses, so the lens is in the reflection mode, right? If I understand from the figure.
Oh, this one is actually in the transmission mode.
Transmission.
So we fabricate it actually on a transparent substrate, so the light can actually pass through.
Okay, and for the, so when it transfers from amorphous to crystalline structures, what is the change in delta K? Because that will absorb the light, right? I mean,
yes. So that's why we are using GSST instead of GST, because if you look at GSST, we operate at about 5 microns. The change of K is actually quite minimal. The K at 5 micron, I believe, is something like 0.0. It's at the measurement error. I mean, it's technically in the error bar. Right. So that's why we have very little loss here. It's bi-state transparent.
Okay, thanks.
So all the loss you see there in terms of limiting the efficiency, it actually mostly come from one is a phase error due to discretization. We only use 4 levels to cover 2 pi, and 2 it just comes from the meta atom. The efficiency is not unity. That's what compromised the efficiency there.
Okay. Thanks. Thank you.
I have a question. Like if say at high temperatures, like more than 200 or 300 degrees centigrade, won't they get oxidized?
Oh yeah, okay, great question. So if you look at, I don't know if I have more. Okay, this is okay. You have to look at the detailed structure here. In this schematic, I'm actually missing one layer on top. I should have corrected the figure. For every time we put on this phase changing materials, we always cap them with a capping layer. Usually it's ALD, aluminum oxide, or sometimes we also use PECVD, silica, and just to prevent any kind of oxidation reactions. Yeah, so you definitely need to cap that to prevent any oxidation reactions.
Also, like when you prepare, how do you take care of these? The small oxide impurities. Won't they affect this transparency, IR transparency? Like because it has to have a flat transparent, right, for a wide range. So if you have any oxide impurity, then won't it affect your transparency? How do you take care of these oxide impurities?
Oh, oxide impurities, you mean?
Yeah.
Okay, sure. So this material is sensitized using essentially a classical kind of melt quench method. So what our collaborator did is not us. Okay, so what they did is started out with high purity components, so like 6-9 components, and they also do a distillation process for all the initial ingredients, so that essentially remove any kind of remaining oxide impurities in the starting bulk. Okay, so the bulk is a very high purity. Now, when we do the deposition, this is also done in a high vacuum environment, so we essentially minimize any kind of oxide impurity coming into the material. What I also want to mention here is that the loss we're talking about for this phase changing materials, it is still much higher compared to what you'll be talking about in optical fiber domain, right? We are talking about, in fiber, you're talking about dB per meters, or dB per kilometers. In this case, the loss is still in the range of dB per centimeters, or even dB per microns, right? So, so the little amount of impurities actually does not cause significant amount of change in the optical properties.
Okay, yeah, thank you.
Hello, Professor JJ. Yeah, first of all, hello. Hello.
Yeah, I can hear you. Yeah. Go ahead.
First of all, thanks for that wonderful talk. So I have one doubt from that meta lens section. So why exactly we need different shapes for each scatterers? It's like by changing the geometrical parameters, we can still control the phase, right? So we have this different shapes actually, like you mentioned, like cross-shaped scatterers and all. So how the shape plays a role in this design?
Sorry, could you repeat the last sentence?
Yeah, I mean, what would be the role of the particular shape actually, other than controlling the phase?
So you're asking about how we pick the different shapes besides the phase requirement?
Yeah.
Okay.
Yes.
Okay. Good question. So the general criteria is that we want them to have small phase error, and also they should have high optical transmittance. So it means that all the light has to go through rather than being reflected, just to enhance the efficiency of the optical component. Now, in the case of a reconfigurable lens, it gets a bit more tricky, right? Because you have to ensure high efficiency in both states. At the same time, you also have to minimize the phase error in both states. So what we did is actually we have developed a field of merit that essentially allows us to account for both phase error and amplitude in both optical states, so that we can do a quantitative assessment of the different designs and pick out the best ones.
Okay.
Yeah,
So,
you can refer to the paper here. We give a more detailed account about the field of merit and how to select all the meta atoms.
Okay. One more doubt in the same area. So what will be the polarization response for this meta lens?
Okay, so for this particular design, this is responding only to linear polarization, because if you look at the meta atoms here, some of them, like this kind of H shape, they only have two symmetry, right? So yeah. So if you want polarization diverse lens, you have to select all the meta atoms that all have four-fold symmetry.
Symmetrical shape. Okay. Thanks.
Like some of the crosses here, right? This is close to four-fold symmetry.
Understood. Thanks. Thanks, bro.
Hello.
Yeah. Yep.
Yeah, Professor Jay, I have a doubt regarding material. Like this, the elemental composition will be same in bulk material as well as thin film, or it will be different? Like stoichiometry will be same or different?
Great question. Okay, it's usually different, right? If you go through either evaporation, especially evaporation process, which is what we're using here, different elements, of course, they have slightly different vapor pressure. So different compounds, they have. So evaporation usually is a kind of incongruent process. Okay, so the way we were able to deposit materials that preserves the bulk stoichiometry is to use a flash evaporation technique. Okay, so what we did is we actually have we customized our deposition setup. So we have essentially kind of mechanical feeder that would release small amount of material every time into a boat that's already heated at high temperature. So that every time we release small amount of material, it's going to immediately get evaporated. Everything get released into a gas phase. So then that preserves the stoichiometry, right? And then next time we then release another small amount of material and then get evaporated again. So that's called a flash evaporation. And the so my student actually put together a setup. It's pretty straightforward. We just you own like eBay, bought like a little mechanical vibrator, control my smartphone, and yeah, we can just control it outside the chamber there. So we retrofit it onto a conventional evaporator. So if you're interested, I can send you some of the details how we actually did it.
Thank you, Professor.
I have a question. Like, so when you this GSST, when you from amorphous to crystalline state, when you give an electrical pulse or whatever way, like what is the crystalline phase actually? What the phase it crystallizes?
Okay, so for GSST, the crystalline phase is cubic. It actually has two crystalline phases. So one is a metastable cubic, the other is hexagonal. So very similar to the kind of the parent compound, right? The GST, germanium telluride. But usually, the different switching purposes, we are mostly talking about the cubic phase, because it's the phase that's amenable to fast switching. But I do want to mention that the crystalline, the cubic and the hexagonal phase, they're actually quite similar in terms of properties. They are just different stacking sequence of the atomic planes. So it turns out they are very, very similar.
So how do you make? How do you like ensure it is a cubic phase in your device actually once it crystallizes? What is the way you find like it's a like a cubic phase?
Okay, So to be honest, if you look at the device, on the device level, we have never really tried to verify that. We used Raman to verify that indeed it crystallized, but we did not go one step further to see whether it's cubic hexagonal or cubic, sorry, is it crystalline hexagonal or crystalline cubic? Okay, partly because we don't care. Okay.
Yeah, but usually anneal and then see the, I mean, it crystallizes to cubic or hexagonal one. But
Yeah.
at device level, I mean, so, I mean, what is the way you can make sure that it's a crystalline, I mean, cubic phase or the other hexagonal phase? There is no way you can find out.
Yeah, you can do that. So a few different ways. So one way is that you can actually use essentially in situ TEM. That's kind of what we did. If you read our paper about GSST, we did actually in situ TEM to looking at essentially the phase transformation during heating process. So we were able to see a transition here. It quickly go to a cubic, and then quickly goes to a hexagonal because the heating temperature was high at the time. So you can verify the structural transition in situ using that technique. Okay, so that's one way. Now, the other method, it's actually more convenient, is to actually use the doped silicon platform. Because we can in situ switch this material on this doped silicon, we can do something like EBSD, right? Or SAED, selective area electron diffraction, on this kind of a little silicon fission materials or suspended on a silicon heater to verify the structure transition in situ. So that's probably the best way to do the switching there if we want to do an in situ characterization of the crystalline structure.
Oh, thank you. Thank you.
Yeah, so that's why these doped silicon heaters, I think they are very useful, not only from a photonic device perspective, but also even for material characterization.
Hello.
Yeah.
Hello.
Yes, I can hear you.
Yeah, I had excellent talk and work. I had a related question. This phase change from amorphous to crystalline, you mentioned using a short pulse, something like 5 microseconds, 25.5 volts. So there would be some specificity about this pulse.
Specificity?
For going from amorphous to crystalline, specificity about the range, about this short pulse.
Okay. So
that will decide that crystallinity, or I mean even the
I see.
end state. Yeah.
Sure. So in terms of which direction you go, it depends on two things, right? One is the temperature you go up to. The other is actually essentially the trailing edge, or how fast you quench down. So if you want to amorphize it, you have to go above the melting point. So this dictates the voltage you have to apply. So in our case, depending on the material, if it's GSST on the doped silicon, we can go as low as about 5 volts to amorphize it. Okay. And then in terms of duration, the short pulse has to be short enough so that, or at least the trailing edge has to be decay fast enough so that you don't induce crystallization again during the cooling process. And for that, it depends a bit on the crystallization speed. Okay? So if for something like GSST, cooling in the order of microseconds is actually enough. So it's a bit more relaxed. If you're dealing with conventional GST material, you will have to do it in the order of 100 nanoseconds. That gets a bit more challenging in terms of thermal design of the heater there.
And there is no control of the substrate temperature. I mean, that would also change.
It does. That's a good point. So if the substrate is a high temperature, of course, it will essentially prevent heat dissipation, and therefore it will change the dynamics there, right? But you really have to go up to pretty high temperature to change the dynamics, because the temperature we're talking about here is at least like 300 degrees Celsius for crystallization and 600 degrees Celsius for melting. So the room temperature fluctuation is not a big deal. But if you're trying to use it for a high temperature environment, like 100 degrees Celsius, you have to take that into account.
Yeah, or it could be under some light, some specific.
Right. That you are exactly right. Yeah. So the laser, if you use very high power, then you have to take that into account. Yeah, thank you.
Hello, Professor.
Yes.
Yes, actually, I also have one question. So, what are the on-chip dispersive optical components that are used in that methane sensing?
Sorry, could you repeat your question? I apologize, you broke up a little bit.
Okay, sir. Sir, what are the on-chip dispersive optical components which are used for this methane sensing?
For methane sensing.
Yes, 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 sir.
Okay, so typically, what if people are doing like spectroscopic detection of methane? What they will usually do is they just use things like diffractive gratings in a free space platform, right? So you have essentially have like a light coming in, strike on the dispersive grating, and then you kind of split the different wavelengths light to different angles, and then use a detector array just to detect the different light intensity. So that's what people usually do. Another technique people are using here is so-called tunable diode laser spectroscopy. And in that case, they just use essentially a little tunable laser and scan the wavelengths across a small range around the absorption peak of methane to detect that. So those are kind of the two common techniques of how people use to detect methane.
Okay, sir. Thank you.
Yeah.
Thank
but we
you,
can also use our own chip spectrometer, right? Like our DFT spectrometer. It's perfectly good for that.
Yes, sir. Like on-chip spectrometer using like arrayed waveguides and
array waveguide gratings. Yes, you can do that. You can do array waveguide gratings. You can do shell gratings. You can
yes.
yeah. So those are things you can do. Yeah, yeah. But the
Okay.
challenge if you try to use that for broadband sensing is that you're actually splitting a light into many channels, right? So you actually kind of compromise signal noise ratio specific to absorption spectroscopy.
Yes, sir. True. Okay, sir. Thank you. So if there are no further questions, then I would like to conclude the webinar. Let's hope to meet in another interesting webinar session. Thank you so much for your participation. Thank you.
Thank you again, everyone.
Yeah. JJ, maybe we can wait for some time and we can discuss. Maybe, yeah?
Sure. Yeah, that'll be great.